Thank you. Hi, everyone. My name is Hedieh Abdollahi from IPM Institute, and I'm glad that I've been given this opportunity. Today, I would like to talk about one of the dwarf satellites of Andromeda Galaxy, the closest one actually, and the IX or and the 9. Andromeda 9 is one of the faintest dwarf satellites of Andromeda Galaxy. In this paper, actually, I examined this dwarf galaxy, focusing on 3 key aspects: photometry, star formation history, and dust. And allow me to provide a brief overview of each of these parts. To understand the evolution of galaxies, we employ a unique approach that involves detecting long period variable stars, which serves as a tracer of star formation history. The selection of these stars is based on their distinctive characteristics. For example, AGB stars are evolved stars in the last phase of their lives. Study AGB stars provide insights into the process occurring in stars with masses similar between 0.8 up to 8 solar mass. The AGB stars are the end of their evolution, so they have reached their maximum luminosity, and it's therefore relatively easy to identify them in distant galaxies. By utilizing the mass-luminosity relationship, it's possible to estimate the star's mass, age, and pulsation duration. To estimate the age of the AGBs, to estimate the age of the galaxy, actually AGBs are very helpful because age of AGBs ranges from 30 million to 10 gigayear. So it would be possible to describe the evolution of galaxies from the beginning of the universe somehow until now using AGBs. And AGB stars actually have exhausted their core mass, their core of hydrogen, and are undergoing nuclear fusion in shells around an inert helium core. During this phase, they experience periodic pulsation, causing their outer layers to expand and contract. LPVs are a specific subtype of AGB stars, which characterized by regular and significant brightness variations over a long period of time, typically ranging from 1000 to 100 or a little more. And these stars actually play a significant role in the chemical enrichment of the universe, as they produce and distribute heavy elements through stellar winds. In this slide, actually is a brief explanation of the methodology which I used to study these dwarf galaxies. Following observations and data reduction, I conducted the photometry assessment. After that, I identified the LPVs and reconstruct the star formation history. And after that, I estimated the mass loss of AGB stars. My research actually was part of a comprehensive survey to observe dwarf satellites from the North Hemisphere. The survey was conducted with the cooperation of Keele University in England and IPM Institute in Iran. Our sample included satellites of Andromeda Galaxy, Milky Way, some transitional dwarfs, and some globular clusters, and a number of objects like and 1, 7, and 9 are studied individually. Actually, we conducted our observations over a period of approximately 3 months in about 2.5 years, due to the fact that LPVs have a period ranging from 1000 to 100. Our time series observations with the INT telescope on La Palma Island enabled us to detect variable stars. The observations were conducted using two filters, V and I, V in visible bands and IS alone in the near infrared bands. And as the AGB stars are surrounded by dust, we specifically choose an infrared filter. Moreover, the peak of SEDs or spectral energy distribution of AGBs occurs around 1 micron, which is approximately around the wavelength range of the infrared filter. The INT telescope is equipped with 4 CCDs, and most objects, including AND IX or AND 9, are limited to CCD 4. Actually, in crowded fields, the acetone photometry package performs PSF photometry. And in AND IX, there are about 8,000 stellar sources in the output catalog of the photometry, of which about 4,000 are within 2 half-light radius. And following the photometry process, we assessed its accuracy using 3 steps. Firstly, we compared actually here we can see the pictures. The first picture, we compared output catalog with other catalogs, observing at similar filters. Our results in the I band are in good agreement with STSS catalog. As a second steps, we compared actually, we used the added star simulation and which added star simulation generates a set of stars. The simulation distributes stars with a specific magnitude randomly in the image. A similar approach to our photometric measurements of the Andromeda 9 was used for the measurement of the simulated stars. The magnitude differences between photometry procedures and simulation magnitudes was assessed. Small magnitude differences indicate that the photometric process has been performed accurately. The third method in a third plot actually is based on estimating the completeness limit. We were able to determine how deep observation and photometry are in different magnitude bins. In this plot, it can be seen that the completeness limit is 100% above the RGB tip, around 21.20 meg. More than 90% of the catalog is complete up to the magnitude 22 meg. And considering that we are looking for variable stars between about 70 up to 22 magnitude between RGB tip and AGB tip, so the catalog was sufficiently complete, and we proceeded to next step, which is identifying the variable stars. And variable stars were identified using the Stetson variability index, and an estimation of variability is based on variation in magnitude and magnitude error in different frames. We specifically selected variable stars with well-defined optical profile and accurate and acceptable light curves from the entire variable stars. Also, these stars were checked to ensure they were not foreground stars. Approximately 50 variable stars were identified among approximately 4,000 stars in 2 half-light radius of Andromeda galaxy. And examples of variable stars is shown in the first plot. So the magnitude variation around the mean magnitude is evidently significant. In second plot, the star is not variable. Okay, and here the figure shows the distribution of variable stars within the combined frame of the galaxy. To reconstruct the star formation history of our galaxy, we selected LPVs within 2 half-light radius, indicating by a blue circle. And in star formation procedures, actually, the AGB stars are in the final stage of their evolution. So their luminosity is directly related to their mass. The stellar mass can also be used to calculate age and pulsation duration. In order to calculate the star formation rates based on stellar mass, age, and pulsation duration in different age bands, we use this equation actually. And according to this plot 8 actually, we can see that we estimated a star formation at 3 metallicity mentioned in other papers. According to chemical enrichment, the lowest metallicity, the pink indexes, represent the star formation rate at the beginning of the dwarf evolution, while the highest metallicity represents the star formation rate at the present time. The star formation epochs occurred between half of the gigayear and 13 gigayear ago, and star formation rates of Andromeda 9 in 3 metallicity reached their maximum in 3 metallicity actually around 6 gigayears ago. In this plot, it's actually the cumulative star formation rate represent that how much stellar mass was formed by Andromeda 9 during each age bands. The total stellar mass was estimated using the star formation rate in 3 metallicity, which is a good agreement with other studies. We also actually examined that the galaxy quenched about 3 gigayears ago, which is consistent with previous reports. 90% of the stellar mass of galaxies formed prior to quenching time. And here's the table displaying the quenching time and the aggregation time for half total stellar mass of IX. One possible scenario for quenching this dwarf is the massive accretion of Andromeda, which occurred about 5.5 gigayears ago. And around the time, most of the Andromeda satellites quenched. And this was also our estimation for Andromeda 9. Besides internal process such as galactic winds, supernova, and stellar feedback, some environmental process are also essential for quenching low mass dwarfs. Factors like tidal effects and cold gas depletion through Andromeda. And our final steps for this dwarf was estimating the mass loss of LPVs. Contrary to supernova dust, AGB's dust directly contributes to a star formation. So there is also a significant difference in the amount of the AGB's mass loss compared to other type of stars. AGBs were actually categorized into oxygen-rich and carbon-rich stars based on the amount of carbon and oxygen in their atmosphere. The dust code was used to model the SEDs of variables for the SED model to be developed. Some input data such as stellar temperature, external radiation characteristics, dust properties like temperature, chemical composition, or grain size distribution, or something like optical depths are required. Dusty assumes a radiatively driven wind when solving hydrodynamic equations for AGB stars. And here, a figure in this figure, we can see some examples of SEDs on the basis of the data we had from the stars at different wavelengths. We fitted a spectral energy distribution. The best fit curves are constructed for two types of dust, actually solid black lines here, solid black lines for oxygen-rich LPVs and dashed black curves for C-rich LPVs. Besides showing the best fits for the preferred dust species, we also show the best fit for alternative dust species, as there were no spectroscopic data available for our sample. We choose to do this. And here, this table actually shows the total mass loss ratio of LPVs in different metallicities. And in all three metallicities, series LPVs contributes approximately 80% of mass loss. This plot illustrates the scattering of the mass loss of O-rich and C-rich AGBs relative to luminosity. Mass loss variance is evident around the RGB tip at a given luminosity or burst mass, indicating a star evolution throughout the galaxy. When a star climbs the AGB evolutionary path, its mass loss increases gradually with luminosity, allowing different mass losses to be observed at same luminosity. Carbon stars tend to have a higher luminosity and mass losses because of the higher masses. However, some carbon stars have lower luminosity and mass losses, luminosities and mass losses than oxygen stars. These carbon stars may be in the interthermal pulses luminosity dip and experience lower luminosity and mass loss rate, whereas after thermal pulses they experience higher luminosity and mass loss rate. And now actually I'm focusing on all satellites of Andromeda galaxies that have been observed in our survey. The photometry
Hedieh,
of the...
could you ramp up? You are running out of time.
Yeah, yeah.
Wrap up.
Yeah, just 1 minute, please. And so for now, actually I'm focusing on the all satellites of Andromeda galaxy, and we actually intended to publish one complete catalog from LPV stars for all satellites of Andromeda. And in last slide, actually, last but not least, I would like to present a brief overview of the recently commissioned National Observatory of Iran. The observatory is located on a Gargash site, and something that is very important about this observatory for now is about the seeing parameter, which is less than 0.6 arcsecond, and it's currently possible to operate 2 observational instruments. That telescope consists of a 3.4 meter main mirror and the Inno lens array, actually, which is suitable for observing low surface objects. And for more information, you can visit the website, and observational proposals are also welcome at the observatory. Thank you so much.